Welcome to the Robotics Brief. I'm Alex.
And I'm Sam. Glad to be here with you.
Today, we're looking at what happens when our AI systems, particularly those for robotics, start getting a seriously long-term memory, not just recalling recent events, but understanding context spanning thousands of steps.
Which honestly sounds like something we should have had already, right? The memory problem feels like ancient history in AI.
You'd think so, Sam, but it's deceptively complex. We're not just talking about storing data. It's about making that data immediately actionable, without a huge computational overhead. It's about leveraging massive past context to improve current decisions in real time.
So it's not just remembering, it's remembering usefully. That distinction is critical, because otherwise you're just bloating the system without gaining anything practical.
Exactly, and the implications are huge. Everything from how robots learn new tasks from a single demonstration to how they navigate complex multi-stage environments without needing to be constantly retrained or rebooted mentally. It's a foundational shift. First up, let's talk about RoboTTT, or Test Time Training Robot Policies. This paper describes a system that scales visual motor context to 8,000 time steps, orders of magnitude beyond current state-of-the-art policies.
Okay, 8,000 time steps. What does that actually mean for a robot on the ground?
It means it can essentially remember and use information from a very, very long period of its interaction with the environment. Imagine a robot learning a complex assembly task or navigating an obstacle course and being able to reference actions and outcomes from an hour ago in its decision-making loop, not just the last few seconds.
So it's not just reacting to what's immediately in front of it. It's building up a much richer internal model of its ongoing experience. That's a huge leap, particularly if they're claiming it doesn't grow inference latency.
That's the kicker, Sam. They're achieving this without making the robots slower to react, which is typically the trade-off. They're using a specific training recipe that allows for this deep context integration without a proportional increase in real-time processing demands.
And what do they say this unlocks, beyond just better performance?
Well, one-shot in-context imitation from human video demonstrations. That's massive. Instead of needing hundreds of examples, a robot could potentially watch one human do a task and immediately get it. Also, on-the-fly policy improvement and robustness to perturbations.
Okay, on-the-fly policy improvement. That's big. It sounds like the robot can adapt its behavior during an ongoing task if something changes, without needing to go back to the drawing board. I mean, if it's truly learning in context, that's what you'd want.
Right. Think of a robot arm building something and a tool slips or a part is slightly out of place. Instead of failing or needing human intervention, it draws on its 8,000 time steps of experience to adapt its grip or motion in that moment.
I'm still a little skeptical about the no inference latency claim, Alex. There's always some cost. It's like saying you can add more memory to your brain without it taking longer to think. I just don't buy that it's zero.
They're not saying zero, Sam, but that it's not growing beyond what's manageable for real-time application. It's about how they structure the memory and recall. They're not brute force recalculating everything. It's more about how the relevant context is extracted and integrated efficiently. They talk about optimizing memory updates for relevant information.
Okay, I'll give them that. But that's a very specific kind of optimization, and it'll be interesting to see how generalizable that is across different tasks and hardware, because robot memory is usually what bogs these systems down.
Next, let's turn to something a bit more concerning: the separation of physical danger from text-level safety in large language models acting as robot planners. The paper is titled, "When Words Are Safe, But Actions Kill."
Yeah, that title definitely grabs you, and it highlights a problem I've worried about for a while. An LLM can say all the right things, but its understanding of the physical consequences of those things might be entirely absent.
Exactly. They're studying whether what they call content danger, like generating hate speech or harmful text, is the same problem as physical danger, where a linguistically benign instruction becomes unsafe once grounded in the physical world by an embodied agent.
And their conclusion?
Through hidden state direction analysis, they show that these two types of danger, content danger and physical danger, form separable signals in LLM representations across several different models, like Qwen and Phi.
So the model might know something it says is bad, but it doesn't register that an action derived from a seemingly innocuous instruction could be dangerous. That's not just a subtle difference. That's a fundamental gap in its safety understanding.
It means that if you're only training an LLM for content safety, you're not automatically making it safe for physical deployment in a robot. You need entirely different safety mechanisms, or at least specifically tailored ones for embodied AI.
This sounds like a huge red flag for the current just plug an LLM into a robot trend. Because people are implicitly assuming that if the LLM says don't hurt humans, it inherently understands what actions could lead to hurting a human.
And this research suggests it definitely does not. It's almost like it has two different brains, one for language morality and one for a spatial physical consequence, and they don't necessarily communicate effectively on what danger truly means in the real world.
So training it to avoid saying kill that person doesn't train it to avoid saying move that heavy object above that person's head. That's a pretty critical distinction, Alex. How do they propose fixing it?
They propose PRISM, a single-layer L2 regularized linear probe to specifically detect and mitigate physical danger by leveraging this separability. So it's a new layer, a separate safety check, focusing solely on the physical grounding of commands.
So it's not addressing the root problem in the LLM's understanding, it's patching it with an external monitor, which is better than nothing, but it feels like we're adding more complexity rather than fundamentally improving the core intelligence.
That's a valid criticism, Sam. It's a practical workaround to a very real and immediate problem. But it highlights how much more complex safety becomes when AI moves from text to physical action. It's not just about filtering output, it's about anticipating consequences. Moving on, we have SceneBind, an omnimodal representation that combines semantic understanding with 3D spatial understanding across vision, audio, and language.
Omnimodal always sounds like a marketing buzzword, but I get the idea. Bring everything together. But the key is usually how you bring it together.
Right. Existing omnimodal encoders are great at instance-level semantics, knowing what is present, like identifying a chair or a dog. But they often lack explicit spatial structure, meaning they don't know where that chair is in 3D space relative to other objects, or what sounds are coming from what location.
So it's not just knowing there's a dog and a ball, but knowing the dog is under the table and the ball is rolling towards the door. That's a huge difference for a robot trying to interact with that scene.
Precisely. SceneBind addresses this by representing each scene as a semantic spatial entity, combining a global semantic embedding with object-centric semantic spatial slots. It's explicitly capturing object-level semantics, spatial attributes, and even uncertainty.
So it's not just a collection of detected objects. It's building a coherent, structured mental map of the environment, including relationships and locations, which is, what humans do naturally.
And they also propose SceneB, a novel neural architecture to learn this. The idea is to have a robot that doesn't just see and hear, but truly understands the 3D layout and the meaning of things within that layout. Think about a robot needing to grasp a specific tool, identified by both its visual appearance and the sound it makes as it clinks against another tool, all while knowing its exact position.
I actually really like this, Alex, because so much of robot perception feels like it's been siloed. Vision models, audio models, language models. They operate independently and then try to stitch together an understanding. This is trying to fuse it much earlier.
Yeah, and the ability to integrate uncertainty is key. Not everything is perfectly clear in the real world. Knowing what you don't know about a scene's layout is as important as knowing what you do know.
That's a smart addition. For robust robot action, understanding ambiguity is crucial. My only concern is, how computationally expensive is this omnimodal representation? Because if you're fusing all this data and creating this rich spatial model, it could get heavy fast.
They don't dive into the real-time implications for robotics yet. It's more about the representation itself. But for complex tasks, this level of comprehensive spatial awareness is almost a prerequisite. It's laying the groundwork, Sam. Next, we're looking at Tell Me Why, Ain't Nothing But a Jam, a system for exploratory causal analysis of urban driving data. This is about understanding traffic patterns and congestion using dashcam annotations.
So, not directly robotics, but certainly about understanding the environments robots, specifically self-driving cars, operate in.
Exactly. Traffic agencies have massive amounts of video data, but most of it is observational. You can see what happened, but it's hard to answer causal questions like, how would rain change traffic density? Because you're not running controlled experiments.
Right. Correlation isn't causation. We know that. So how does Tell Me approach this?
It starts from a structured event table built from dashcam annotations. So it's converting raw video into discrete events. Car changed lane, pedestrian crossed, rain started. Then it combines causal structure learning with the PC algorithm, bootstrap-based stability checks, and query-specific effect estimation.
So it's trying to infer the cause and effect relationships from observational data, even without interventions. That's ambitious.
It is. It's essentially trying to build a causal graph of traffic dynamics. So instead of just saying traffic slowed when it rained, it aims to determine if rain caused the traffic to slow, and by how much, controlling for other variables.
Which is incredibly useful for city planners and traffic engineers. If they know rain causes a 20% slowdown because of X, Y, and Z, they can plan interventions.
And for self-driving cars, knowing the causal chain of events under different weather or road conditions could allow for much more intelligent and predictive navigation rather than just reactive. It's about understanding the underlying dynamics of traffic, not just its current state.
Yeah, but causal inference from observational data is notoriously tricky. There are always unobserved confounders that can throw off your conclusions. How confident are they in their causal claims?
They use bootstrap-based stability checks to try and quantify the robustness of their causal links. It's not perfect, but it's a systematic approach to explore these causal relationships where running real-world experiments is impossible or unethical.
Okay, so they're trying to put some guardrails on it. It's a pragmatic approach to a hard problem, but I still think you have to be very, very careful about claiming true causation when you haven't intervened.
Finally, let's look at online neurospace-time memory for dynamic novel view synthesis. This one brings us back to that memory problem we started with.
Novel view synthesis is generating new perspectives of a scene, like creating a 3D model from 2D images. And dynamic means the scene is moving, so making a 3D model of a moving scene in real time.
Exactly. The fundamental trade-off here is maintaining a persistent, long-horizon memory to reconstruct temporally occluded regions while operating under strict real-time constraints. If something moves out of view and then reappears, you want the system to remember it, not rebuild it from scratch.
But if you keep all that memory active and updated, it gets computationally massive very quickly, especially with dynamic scenes, where everything is constantly changing.
And that's where test-time training, or TTT, comes in as a powerful memory mechanism. But standard TTT models mandate gradient-based memory updates at every frame to adapt to changing motion. That cost is what precludes real-time application and can lead to instability over long contexts.
So the existing TTT methods are too heavy because they're essentially relearning or re-optimizing the entire memory at every single frame, which just bogs down the system.
Yes, this paper argues that memory updates are more demanding than memory usage. They propose separating memory updates from memory usage.
Ah, so they're decoupling the read and write operations, in a sense. You can still access the long-term memory instantly, but you don't have to rewrite the entire thing every time something changes.
Precisely. They're trying to find a more intelligent way to update the memory. Instead of a full gradient descent on the entire memory structure at every frame, which is computationally prohibitive for real-time, they're looking for sparse, efficient updates.
Which makes sense. Only update the parts of memory that are actually relevant to what's changed in the scene. It sounds obvious, but actually implementing that efficiently without breaking the coherence of the memory is the hard part.
And that's what they're tackling. This could be hugely impactful for any robot operating in a dynamic environment, like a self-driving car in traffic, or a robot navigating a busy factory floor, where remembering a consistently accurate, up-to-date 3D model of its surroundings is paramount.
It's all about making that long-term context useful in the moment without drowning in computational cost. It's a recurring theme today.
So, Sam, if we step back from these, it feels like we're seeing a push on two fronts: making AI systems truly remember and reason over much longer timescales, and critically, how to make that memory safe and spatially aware in the physical world.
Yeah, it's memory and grounding. That words are safe but actions kill paper, for me, really underlines the fact that as we give these systems more context and capability, the consequences of their actions become much more serious, and the safety measures need to be tailored to the physical domain.
And the Robotti work shows us the potential of that extended memory. It promises capabilities that seem almost human-like in their ability to learn from single examples or adapt on the fly. But that capability also heightens the risk if the system doesn't grasp the physical reality of its actions.
It's a balance, isn't it? The more powerful the tool, the more careful you have to be with it. We're giving them more history, more context, but are we giving them more wisdom?
That's the open question, Sam. Can we teach wisdom or just better data retrieval? That's it for the Robotics Brief this week. I'm Alex.
And I'm Sam. Thanks for tuning in.
We'll see you next episode. Take care.